So, we have looked at the integral form of the momentum equation. We have established that how the boundary layer thickness comes out to be almost the same as what we got through our normal similarity transformation. The variations are obviously the same. So, in this particular class what we are going to do, we are going to look at the integral form of the energy equation. That is what we are going to do here. Okay. So, once again, as we know that there are two forms. So, these are the two profiles, one can be delta, one can be this. So, we are assuming that this is delta, this is delta t, and the wall is T wall. Okay. This is T infinity. Okay. So, our basic assumption is that delta is greater than delta t, okay, which is usually the case. As we said, except in liquid metals and other things, this is mostly the common type of fluids will actually follow this kind of a profile, right. Okay. So, delta is greater than delta t. Okay. So, u dt dx plus v dt dy, that was the expression that we initially had, right. So, t as y tends to infinity is basically T infinity, T at y equal to 0 is Tw, right, that is the wall temperature. Okay. Once again, let us write it in a conservative form. Okay. Got it. So, now let us integrate. Got it. So, this was the conservative form of the energy equation, that means you include the continuity, okay, and this is we are integrating it with respect to y once again, that is what we did earlier. So, once that is done, okay. So, this is equal to 0, right, which is basically true because at 0 now we are not considering suction and blowing, we have already written. If you want to write it in a proper form, that can also be done. Okay. So, you can still continue in that particular way, but here V is equal to 0. So, that is what we have taken. Okay. So, this is also equal to 0 for the same reason, because the thermal gradient disappears as we move to the free stream, right. So, this is basically no blowing and this is basically the free stream, right, free stream, the gradient vanishes, right. So, these were obvious to you. So, now what we can do is that we can now write this particular expression, the revised form of the equation now as got it. That is a revised expression, right. Of course, looking at the nature of this particular term V t delta t and T delta t, we need to find out what this term is all about, right, that is what that term is. So, for that we would need to use the continuity equation, right, we can use the continuity equation for this. right. So, V delta t is basically given as 0 to delta t du dx into dy, right. So, that is the V delta, because we needed that expression which you can substitute it there, right. Okay. Of course, T delta T you already know what T delta T is going to be, correct. Okay. So, if you do the so now that you have got this particular expression ironed out, okay. Now, how to proceed to the problem? So, this particular expression, you remember that this is given, that the velocity at the edge of thermal boundary there, right, that is what it is, correct. Okay. So, now okay, so to we can once again apply the Leibniz rule over here to this particular guy. Okay. If we do that, then what we get is V delta t will be given by d by dx 0 to delta t u dy minus u delta t d delta t by dx, right. Okay. So, now we take this value of V delta t and substitute it here, right. We have to substitute it there. So, let us look at once after substitution what happens. So, the first term remains the same, plus t infinity minus d by dx y equal to 0, right. Okay. So, let us take term by term, so that we can, it makes a lot of sense to do the math properly. The first term, let us do that. Okay. So, the first term can be written as, again applying Leibniz. So, you can see how the Leibniz is coming in handy, right. So, applying Leibniz we can get this. I am not writing the 0 boundary condition anymore, which was a part of Leibniz, because you already know that that is going to be 0. So, that is the first term that we get. Okay. This particular term, so that was this term only, this particular term now can be written as, that is the second term of the series, right, can be written as d by dx 0 to delta t u t infinity dy minus 0 to delta t u dy dt infinity by dx, right. So, that is also that the second term that we are actually writing over there. Okay. So, now that we have finished writing these two terms, okay, now let us kind of assemble things a little together, okay, because we have all these terms spread all around. Assembling, you should practice this algebra in your leisure time, just so that you know. This is basically algebra, this is not much of a complicated math either. Right. So, that is the total temperature profile that you get. Okay. Choose these are the boundary conditions. Okay. And similar to the velocity boundary condition, right. So, similar to all these boundary conditions we get this also. So, choosing the temperature profile, then putting in the boundary conditions, we get this. So, if you now go through the math by putting in all these boundary conditions, I've already shown it for the velocity boundary layer. There is no reason to show it once again, reiterate it once again for the temperature boundary layer, that how you actually find them, right. But you can readily see, depending on our boundary conditions, this is the T wall temperature, 1 minus 3 by 2 y by delta t, very similar to the velocity boundary layer, except that it is a 1 minus because of the opposite nature of the slope, right. So, that is what you get, right, if you plug in all the numbers, right. Okay. Now, if delta is equal to delta t, okay, the velocity solution is valid within the thermal boundary layer, right, is valid within the thermal boundary layer. That was the assumption that we made initially also, okay, because it is a thick velocity boundary layer. So, whatever the velocity solution was is kind of imposed on this as well. Okay. So, what we need to do now is that we need to pass on this temperature profile, okay, inside the full temperature that we got here. Let's call this equation A, right. That is where we need to substitute, okay. And we already have the velocity expression ironed out, right, because your u was already kind of known, right. So, it is not very difficult to do this, okay. So, we are not going to go through the whole math steps for that. We can just write down some of the expressions that we have. Okay. So, if you evaluate all these integrals and other things, okay, what you will get is as follows: d by dx, okay, u infinity delta t delta, let us put a bracket here, or let us make this bracket okay, so that this can become now a third bracket, okay. So, this is delta t by delta square minus 3 by 220 delta t by delta to the power of 4, okay. Close this bracket, is equal to 3 by 2 alpha by delta t. That is all that you get, okay. Okay. So, that is all that you get after you substitute these expressions and if you evaluate. So, basically you have to put in u by u infinity that we already found out, and this particular guy over here to the previous expression, and you just need to go through the motion. Now, of course, here there is a problem because we have now two variables, delta t and delta, okay, to make things a little bit more dicey, right. So, in order to avoid that, okay, we already know that delta is greater than delta t. So, it is very natural if you compare these two expressions, for example, right, which is delta t by delta, we know that the fourth order term will be much lower, right, than this. This is 3 by 20, that is 3 by 280. So, there is a 1 order difference right there, right, and on the top of that this is squared, this is to the power of 4. So, naturally there will be more such variations over there. So, you can safely assume that 3 by 220 delta t by delta, okay, delta t by delta is much lower than delta t by delta to the power of 4 is much lower than 3 by 20 delta t to the power of delta square, okay. So, that is already an assumption based on the fact that delta is greater than delta t. So, based on that, okay, so this simplifies, equation simplifies, 10 alpha over delta t is equal to u infinity d by dx delta t by delta square close bracket. We already know that delta is given by 280 by 13 gamma x by u infinity, that comes from your velocity or / momentum analysis that we did, Okay. Okay. And of course, the other boundary condition is that delta t at x equal to 0 is equal to 0. So, that is the starting point. So, the solution of this particular expression becomes delta t by x is 4.528 into Prandtl number to the power of 1/3 Reynolds number to the power of x to the power of half. Okay. So, that is the expression that we get, okay, delta t by delta. Now, we already know Nusselt number is defined as h x by k and h is defined as k. Just to recap, dt y equal to 0 divided by T s minus or T wall minus T infinity, not T s, right, that we already knew, right. So, now it becomes a very simple thing that h x then becomes 3 by 2 k by delta t, right. Okay. So, our h x becomes 0.331 into k into x, okay, Prandtl number to the power of 1/3 Reynolds number to the power of x to the power of half, right. And Nusselt number becomes 0.331, it is the same, remains the same, Prandtl number to the power of 1/3 Reynolds number to the power of half, right. Okay. So, so this is actually very close to the error is actually less than 2.4%. The error less than 2.4%. So, you can imagine that it is a very robust way. So, all we have done is that we have got this expression, okay, and then we just substituted for delta, okay, and then we just integrated the whole thing, okay, which gave us this particular form, which preserves once again that Prandtl number to the power of 1/3 Reynolds number to the power of half dependence, and factor sits in front. The error is less than 2.4% compared to the similarity, right. So, I think it is a very powerful tool, as you can see, without doing much of a thing, okay, we are able to get this perfectly fine result, right, using just this kind of analysis. Okay. Now, we will, this is we did for the constant wall temperature. We can also do the same for the constant wall heat flux. Okay. I am not going to do the full thing, but what I am going to do is that I am going to pose the whole thing, and it will be left up to the students to follow it up in the form of an exercise. Okay. So, uniform heat flux, that would mean that it is the same plate, okay, the same type of boundary layer is growing, except that instead of a temperature, fixed temperature, you constantly give a constant heat flux Q. Okay. So, that means you have put it, say, for example, on an on a heater, okay, and the heater is connected to a power supply which supplies a constant heat. The previous case, you can consider it more to be you are placing it in an isothermal bath, right. So, that you have keeping the plate, no matter what, the temperature is always kept at a constant level, right. So, that it is always in equilibrium with each other. Okay. So, so this is how you are transferring the heat. Okay. It can be anything, it can be Qs double prime, say for example is the heat. Okay. So, once again the integral formulation, once you write it, that does not have any such problem, right. So, you can easily write the same thing in the same way that you did earlier, 0 to delta t u t minus t infinity dy, right, that is what you wrote earlier, dt by dy evaluated at y equal to 0, right. This expression still remains the same, there is no problem with this. Okay. Your velocity profile also remains the same. So, I am giving you the hints, the velocity profile still remains by delta minus half y over delta cube, right, all this thing remains the same, got it. Okay. Only the expression for h now has to be recast in a certain way. So, instead of that we are writing it in this particular form, wall minus t infinity, and Nusselt number is Qs double prime into x divided by k t wall minus t infinity, right. So, these are the two expressions, slight change because of the constant heat flux condition. Okay. You can once again assume the temperature to be the same, B naught plus B 1. If you do not want to write it in ABCD, you can write it in this way also. Y cube, etc. Okay. So, boundary conditions now are k dt by dy at y equal to 0 is equal to q s double prime, the first boundary condition. Second boundary condition is at any x and delta t, it is equal to T infinity, which is also not difficult to once again dt by dy, okay, at y equal to delta t is equal to 0, and d square t by d y square at y equal to 0 is equal to 0, right. So, these are the boundary conditions, the 4 boundary conditions that we have. Okay. So, applying, so what you need to do is follow the motions after this, that you need to apply the boundary conditions to find out what the temperature profile is going to look like. Once you get the temperature profile, it can be easily substituted now into this T minus D infinity expression, and you can find it. So, I will just give you the temperature profile finally before we wrap up. Okay. So, what we can see over there is that if you substitute all these things, the temperature profile will look T infinity plus 2/3 delta T minus y plus 1/3 y cube by delta T square q s double prime by k. That is the expression that we get. Okay. Now, surface is set, if you put y equal to 0, the T wall temperature becomes, okay, T infinity plus 2/3 q s double prime by k into delta T. Okay. This is the wall temperature. If you put y equal to 0 here, you will get this, right. So, based on these two expressions, okay, now you are in a position, right, because your wall is now taken care of. Okay, you know what is your wall temperature going to be. Now, you have to you have to do is to substitute this expression in the parent equation and try to see that what will be the final number, right. So, the final expression, if you manage to do this properly, will be 3.594 Prandtl number 1/3, Reynolds number half. So, the coefficients do change a little bit. Okay. The coefficients do change a little bit, but this variation still remains the same. This of course remains is a different number now, right. So, that is your delta. So, that means when you invert it, you are going to get a different expression, a lower expression for your Nusselt number, right. So, based on this, your Nusselt number should be, if you do it properly, it is going to be 0.417, that is a higher value. Okay. So, Reynolds number to the power of half. Yeah. So, the Nusselt number will be a little higher because this coefficient is a little lower. Okay. So, that is the reason why you should have your Nusselt number a little higher. Okay. So, what we have done, we have shown that for the two sets of conditions, constant wall temperature and constant wall heat flux, okay, it is possible to cast the expression in a very similar way, right. So, let us just recap what we just did. Let us take the momentum equation. What we have done is that we saw the momentum equation, right. What we did is that we integrated out the y variation completely, okay, using Leibniz rule and using the pre-existing boundary conditions. We integrated out the whole thing, right. As soon as we were able to integrate out the whole thing, okay, we got an expression which had only depended on x, right. So, there we substituted and solved, we assumed a velocity profile, okay, a velocity profile which depends on y, and then once we did the integration, okay, we found that what will be the delta, okay, that means the boundary layer thickness. Once we knew delta, Cf and all the other parameters, we can determine it very easily. Now, coming back to the temperature profile, a basic assumption is that whether is delta is more than delta T, which is the most common type of fluid that we see, that delta is more than delta T. Using that expression, okay, what we did, we started with the energy equation, substituted the velocity, assumed a profile for temperature, again integrated the whole thing out, and finally found out how delta t varies with respect to x. And once delta t is known, as we know, the h, the heat transfer coefficient, is inversely proportional to delta t. So, we were able to knock out the heat transfer coefficient, and Nusselt number is nothing but the heat transfer coefficient minus the, it is a non-dimensional number. So, we got the correct expression for that too. Okay. So, it is a very simplistic approach by which we have assumed, central piece is that we have assumed polynomial for both velocity as well as for temperature, right. And this polynomial made sense because we were able to satisfy all the boundary conditions. In fact, that is how we found out the coefficients of the polynomial, and we found that the results that we got varied by less than 5%, right, with the actual similarity transformation, which was very difficult, which involved a lot of math and other things. This is a very simple integration, just a straightforward integration. Okay. Substitute the values of the y, that means a variation with y, integrate out with respect to y, and you get an expression which is a function of x only. Okay. So, in the next class what we are going to do, we are going to look at some of the special cases which we alluded here, that there can be suction and blowing, there can be something called a wedge, which seems to be a little different from what the flat plate boundary layer is. So, we kind of just touched upon that. Next class what we are going to do, we are going to look at the general case of suction and blowing, and after that we are going to look at a new class of solutions which is called Faulkner scan, which is basically valid for these wedges, okay, those wedge inclined plates and things like that, where the free stream velocity is a function of x. So, that means there will be a pressure gradient within the boundary layer. Okay. So, see you next class.